Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Today, we are going to finish up what we started last time, which was pretty much about SQL. And then we'll start with cloud storage. We'll start storing things in the cloud, and I'll show you how this is actually made on the high level. Before we start, I will ask you one question to see if you followed last time. I'm going to switch over to this screen. And my question is the following. Which one of these is not a fundamental shape of data? Cubes, tables, trees, circles, graphs. 4 of them are fundamental shapes of data, and 1 of them is not. So as a reminder, you can participate both from the lecture hall and also from Zoom. See where we stop. Right, let's see your answers. Circles wins the majority, and indeed, it's circles, because we saw that we have tables. That's the relational tables that we are brushing up right now. Then we look at the trees the entire semester. We'll see it's a denormalized version of tables, but I'll explain what that means. Then we have graphs, which is a generalization of trees, but you can have cycles, so it's much more complex. And cubes, which are for business analytics, which is even more highly structured than tables. Thank you very much for this. So now and congratulations for the right answers. Now I'll switch over again to my slides. And start right away from where we left. So as a reminder, last time I explained to you that in the relational model, which is the fancy name for a model for tables, we have rows, we have columns, and some of the columns can identify the rows, right? Synonyms for row are records, tuples, business objects. So there's plenty of ways you can call rows, but basically this is a thing that you model. And then in the columns, you have the properties of whatever you store in there, like first name, last name, and so on. In essence, a table is a set of rows or a list of rows if you want to preserve the order. Then what I showed you is that there is something called the relational algebra, which manipulates tables. Just like with addition and multiplication, you manipulate numbers. You can also do things similar for tables. We saw that one of them is selection, where you select some of the rows based on a criterion. For example, all the people in Switzerland. You can project, meaning on the columns, meaning that you take, for example, first name and last name of all the people. Then we saw that you can group things. This is to aggregate. For example, you have a list of the population by city, and you can aggregate by content. This is a group by. Then you can sort. If you have lists of rows, if you have sets of rows, of course, you cannot sort because sets don't have order. But if you consider a table as a list of rows, then you can sort with a specific criterion. And then we saw that you can combine tables together. And this is done by matching columns. For example, you might have, I don't know, if you're the tax office, you might have a list of persons with their address and city and so on. In another table, you have the list of tax returns, several per person. But every tax return has a column that might contain the social security number, and that points back to the other table with the persons. What you can do is then join these two tables, meaning that you're going to create a wider table with all the columns, first name, last name, address, social security number, and also the tax return, all joined together. Which brings me to normal forms. Normal forms, I would describe as best principles for how to store your data in tables. Because if you don't know these principles, you might do it wrong. And the way you will notice is that you're going to have what is known as anomalies. So I'm not going to go into details of that. If you're interested, you can find them in Information Systems for Engineers. But what that basically means is that if you don't pay attention to the way you design your tables, you might end up with redundancies because you store the same thing multiple times. But even worse than that, you might even end up with conflicts that you might store in different values the same thing. And then you have a problem because your table is just inconsistent. And these issues, when you have redundancy, can create conflicts when you update data, because you might update it here, but you forget to update it there when it should be kept the same. It can appear when you delete data, that you delete too much data if it's not poorly stored, and it can happen when you insert data. For example, you might insert a tax return, but you don't have any matching person, and so on. So these are the anomalies that can occur, but there is a very intuitive way of understanding how to avoid these things. And I don't want to go to the details. You will very soon understand why I'm not going to the details. But basically, what it means to design a relational table well, or a relational database well, is that the golden rule is one table for everything that means something. It means one table for the people, one table for the tax return. For example, at ETH, if you have my studies, it's probably one table of students, one table of lecturers, one table for the lectures, one table for the exam results. So good design means you properly separate in multiple tables, and then you can join them back if you want to join them back. So this is the general principle. But there is something known as the first normal form that you start with, and this is something I told you last time. The first normal form is only another name for what I called atomic integrity. Remember, no table in a table in a table in a table like this. This is forbidden, right? This is called atomic integrity. And if you respect atomic integrity, this is called the first normal form. You are not allowed to put tables inside the sets. This is not allowed, this is allowed, right? So this is called first normal form or atomic integrity. Now, the reason it's called first normal form is that there are other normal forms where you keep being more demanding and have more requirements for the good design. So there's the second normal form, there's the third normal form, there's the fourth, the fifth, the sixth, and so on, right? But of course, this is more advanced, and we go into these details more with computer scientists. For the purpose of information systems for engineers, so the other lecture, we only look into one besides the one with the tables in the tables forbidden. And this is called the Boyce Code normal form. Oh, I had counterexamples. I can show you that as well. So still the first normal form. This is not allowed because you have tables in tables. You cannot do that. And the way you do that is that you just move them out by duplicating these, right? So this is equivalent. You can look at it offline and convince yourself that this and this stores the same data, except that here you have nested tables, which are undesirable in the first normal form. And here you no longer have nested tables, so this is in the first normal form. Now, the other one, and this is the one we look at in information systems for engineers, it's called Boyce Code normal form. Why? It's just the name of the two people who invented it, Boyce and Code. By the way, Code is the same who invented the relational model in 1970. So what do we forbid in the Boyce Code normal form? We forbid to have dependencies between the columns except for the primary key. So I'm not going into the details of that, but basically here, what we don't like is that we have, the city and the state uniquely determines the postlight sal in there, right? We don't like that because it determines part of the columns, but not everything. So this is undesirable. How do we solve that? This is exactly as I told you, you have multiple tables, right? You just split into multiple tables. And here, this city name that used to determine the postal code, we just take that apart in a different table, the city state with the postlight code. Now, these are primary keys. They determine the postlight code. And now you can join them back if you want by matching this and that column. But now we have nicely separated into two tables, right? So I repeat, to be very clear, just two things to remember. The first normal form means you cannot have tables in tables in tables in tables in tables, also called atomic integrity. And the Boyce Code normal form, very roughly, means that you need to split your tables into multiple tables to avoid undesirable dependencies in there. Now I have very good news for you. The reason I told you not to worry too much about this is that we are going to throw all of that away. We don't care. In this lecture, in Big Data for Engineers, we are going to not want to split into multiple tables. We are totally fine if it's all in a gigantic tables with a lot of redundancies and so on, but that's okay for the purpose of this lecture. So we are going to throw away the Boyce code normal form, going against all principles that I've told you in the information systems for engineers. But even worse than that, we're even throwing away the first normal form in this lecture. We will even allow tables in tables in tables in tables. We'll be totally fine with that, right? And we'll spend weeks on that, so you'll have plenty of time to actually understand in details what it means, right? So again, the only reason I told you that there are normal forms, which are best principles for relational database systems that you run on servers, the good old ones from the 70s, but in big data, we just cannot afford it anymore. Right, and it has to do with the massive amounts of data that we are reading, and so this is why we give up on these normal forms, right? So if you need to remember two things, we are going to have tables in tables in tables in tables during the entire semester, first, and second, we are going to have wide tables, gigantic, in a single table, a single collection, rather than splitting our data amongst multiple tables. These are the two things that are the takeaway messages for this, right? Now, I told you can manipulate tables, but this was all theory. That's the sort of things you do on paper. And there's plenty of fancy Greek letters, for example, sigma for selection, pi for projection, gamma for grouping, and so on and so on. Don't need to worry too much about that. But of course, it's not very convenient if you just write LaTeX formulas to manipulate your tables. It's not practical, which is why there is a language that was invented. It's called SQL or SQL. A lot of people say SQL. That is used to manipulate relational tables. And the good news for you is that it's super easy to learn. And you're even going to have exercises right this week on a notebook to make sure that you master that. It's super easy to learn, even if you're not a computer scientist. It was designed to be natural. So we have all these languages, this ecosystem of languages, and what you need to understand is how they differ. So we have the software engineering ecosystem. It's Python, Java, C++, C, and so on, and even assembly code, right? But this is not in this lecture what we are doing. Even we'll use a bit of Python, but in a very specific context. This is the database part where we have functional languages. We have all the high-level languages. It includes SQL, but it also includes others. We will see in this lecture. These are the super easy to learn fancy languages that are powerful and manipulate data. Then we have the lower level languages. It's a bit like assembly code, right? So not very easy to use. And this is why we use Python typically with these low level languages. But the main reason I'm going to teach them to you is that it's still useful to know, to understand what's going on, right? But in the end, you're going to be using the high level, the nice high level languages. And I hope you will see how convenient this is. So this is the focus of the course, this. And then there's the machine learning. That's not the focus of the course. And here too, we have TensorFlow, PyTorch, and so on. So there's plenty of low-level ways of doing machine learning. And we have higher level languages for that on the way. So people are also working on that. But this is not part of the lecture. This is not part of the lecture. We're just going to look at high-level and low-level database query languages. Okay. All right. But what about SQL? Go back to the 1970s. So this is Don Chamberlain and Raymond Boyce. These are the ones behind the SQL and the first implementation. In the very early days, it dates back to the 1970s. This all was done in San Jose, in California, in the Almaden laboratory that's of IBM. And they basically implemented the ideas of Edgar Code. Remember the idea? Data independence. People should just see and deal with tables, right? So they implemented it. It's called System R. And the language that was used in that commercially available software was SQL, Structured English Query Language. So the goal was to be easy to learn and to look like English. So it was the first commercially available relational query language. And you have their first customer there, Pratt & Whitney, in 1977. So you see now that was almost 50 years ago. Which is quite impressive, right? So this was the first relational databases. Now it's all over the world. I don't know a single company that doesn't have a relational database system installed, right? And some of the companies, so another one called Software Development Laboratories, went all the way to be known actually for 30 years now as Oracle. Who knows Oracle? A lot of you, right? So this was one of the first relational database companies, but now we also have Microsoft, IBM. These are the big three and plenty of open source as well, MySQL, PostgreSQL, and so on and so on, right? Okay. What's important here is what makes it easy to learn is that unlike Python, unlike C++, unlike Java, in a declarative language, you say what you want. The difference between declarative and imperative is just like going to cook for yourself at home, where you just follow the recipe and so on. That would be like Python and C++. It's a recipe-based thing. You tell the computer step by step what to do, right? So that's the recipe. The functional language, declarative, is like going to the Mensa. You go to the Mensa, you take your menu, and that's it. You ask for what you want. So this is the declarative. SQL is like going to the Mensa. Python is like cooking at home following the recipe. For whom is that clear? Right? That's the difference between declarative and functional. And you will see that declarative languages are much more compact and easy to read than imperative languages. Now, bit of warning, there was a trademark issue back then that they couldn't keep calling it SQL in that way, so structured English query language. So they renamed it as SQL, but SQL. And in fact, this is the reason now why you might hear some people say SQL and you might hear some other people say SQL, right? So it's fine to say it in both ways. You just need to know that it's the same thing, really, whether you say SQL or SQL. I tend to say SQL because I was in contact with many of the people who are from the community, so I kind of got into the habit of that, but you can call it whatever you want. But in my experience, a lot of my students start also saying SQL after a while, just as a warning. Okay, who would actually say SQL? Okay, who would say SQL? Okay, some shy hands. All right, get a feeling, half-half. Okay, so SQL is a declarative language, meaning that you say what you want, you say what kind of table you want, how you obtain it from other tables, and the way it's executed, physically implemented, you don't really care as a user of a relational database software. This is the data independence principle. You don't want to bother the users with the details of that, right? But the good side of that is that if you want to go to large scales in the context of big data, from the perspective of the user, it doesn't change anything. You can go to parallelize things on multiple CPU cores, on multiple servers. The user will just keep typing SQL. That's it. Doesn't change anything. The tables will be bigger, it will be faster, but it doesn't change anything to the logical model. So this is what's super important. SQL is also a functional language. It means that you can nest expressions. You can create tables and then use that tables nested in another expression. It's just like in math, right? Addition and multiplication nests too. You can say 3 plus 2 times 5, right? So you nested 2 times 5 inside an addition. It's the same, right? You just have tables instead of numbers. So you can nest the expressions. But now I have made you wait long enough. This is what SQL looks like. Here we have a query that is a selection. It selects the rows where the last name is Crusher. So you say select everything. So it means all the columns from persons, that's the name of that table, where the last name here is Crusher. So you see, this is the one. So what it's doing, it's returning a table here that only has the matching rows, the entire row, matching last name Crusher. For whom is that clear? All right, who agrees it's easy? Right, it's easy to type. You can type it in the Jupyter notebook, and this will appear magically on your screen right below your query in the exercises. Okay, here's another one when instead of the star, you can select the columns you want. So you can say, I want first name and birth date. That's called the projection, right? So that's going to pick first name right here and birth date right here, right? So this one, and you only keep these two and the rest you just throw away. So this is another example of SQL. You can rename columns if you want. You can use the as keyword. It's natural in English. Select the first name as who, you just change here, and the birth date as when, and you change the name right there, okay? Then you can order. This means that you assume an order, right? But this is the case in most relational database systems. PostgreSQL, for example, they do order the rows. So you can say order by birth date, and you see now it's nicely ordered in this way, right? 2230, 2233, 2324. All right, so you can order. You can group by. This is the aggregation I told you about. You have the population for each city and you aggregate by content. So in that case, we aggregate by century. right? So we have 23 and 23 that go together, 24 and 24 that go together. And so you have 23 and 24. And what do we aggregate? We count how many rows. So there's 2 here and 2 here. So this is why we have 2 and 2. This is a group by. Okay. Then we have a way to filter after the group by. For example, here we have 23 and then 24, 24, 24. So we have 2 groups, one with 1 and one with 3. We only want the groups that have more than 2. So 23 goes away because it doesn't fulfill this constraint here. We only keep 24 here. So this is why we only return 24. Okay, this is having. In fact, having is similar to where, right? It's just that where is what you use before you group, and having is what you use after you group. Okay. You can combine them right here to keep simplicity. I just showed one at a time: selection, projection, renaming, ordering, and grouping. But in fact, you can have gigantic queries with everything. Select, from, where, group by, having, order by, and so on and so on. You can even use limits to only have the top 10, for example, limit 10 at the end. Okay. So for some of you, you already know it. And if you don't worry, because the TA team designed exercises for you, right, that you can execute on your laptop. You're going to have a Jupyter notebook with plenty of samples, and you can write your own SQL queries. Please take the time to make sure that you get familiar with the language, right? It's really easy to learn, and the fact that it's interactive in the notebook makes it even easier to learn, right? So please do it if you didn't know SQL before. Make sure you use it, because we'll see it again in that lecture in the context of big data, right? But in this exercise, it's not going to be big data. It's just going to be PostgreSQL within the Docker. Okay. Then the other sort of things you can do is union. What does it mean? It's just that you take 2 tables with the same columns, right? So here it's all the same columns twice: warp, name, last name, and so on. And union means you basically put them in the same bag. So with the set semantics, so here there's only 5 and not 6. This is because there's duplicates, right? So we have enterprise C that is twice, and it's all the same thing. So this is why it's only it's deduplicated. It only appears once here. That's a feature of doing a union. Okay. And then you can join tables. This is when you are in normal forms and you very kindly split across multiple tables to follow the golden rules of higher normal forms. So we have a table for persons here, and we have a table for spaceships. But you probably noticed here that a spaceship has a captain: Kirk, Picard, Janeway. And we can look up the captain with the name over there, here: Kirk, Crusher, Janeway, and so on, right? So you see that Kirk, for example, is linked with Kirk and Kirk here. Joining means that you look for all relationships: Kirk and Kirk, Kirk and Kirk, Janeway and Janeway. So there's 3 relationships in there. And when you join, you just list them and you have all of the columns. This is a join. If this isn't intuitive, just try it out in the notebook for yourself and see how that works, right? So you say persons join spaceship, and then you say what your joining criterion is. In that case, the person's last name must match the spaceship's captain name, right? These are the joins. And you can also deal with the case that there is no correspondence. For example, Crusher is not a captain, so she's not in any spaceship. Then you fill with nulls. And you have a spaceship here with Picard, but Picard doesn't appear here for some reason in that table. Then you just fill with nulls, which basically means empty. There's nothing. It's just a special value for nothing. And you can just, with a few words here, full outer join, that's the fancy name for that. If you say full outer join, then it keeps the items on both tables that do not match anything and fills the rest with empty cells. For whom is that clear? Right? We're just matching captains to spaceships. That's all we are doing here. And then there's the easy case where the column names are the same for what you want to join on. For example, if you have the same column name here and here, then it's just a natural join. You don't even need to bother saying that you match this with this, because it's going to assume, the system will assume that you match the columns with the same names, right? Okay. And this is then the advanced part, but this is once you have really made yourself familiar with a single select from where, then you can put a select from where in a select from where in a select from where. It's the same idea of nesting, right? So it's just like you do addition in multiplication in addition in multiplication. You can also do the same when you manipulate tables. Okay. This you don't need to worry too much about. This is just so you know that behind the scenes, people actually use these fancy Greek letters, but this is more for the people who implement the whole system, right? They come up with an internal mathematical representation that you don't need to worry about for the purpose of this lecture, right? I have other curiosities here to bore you with. There's the fact that, you know, in Boolean logic, it's true or false, right? Either it's raining or it's not raining, right? Either a cat is black or a cat is not black, right? So, but in SQL, it's three-valued logic, there shouldn't be an S here, meaning that it can be true, false, or it can be unknown. So we have a third special value that says unknown, right? And then you have this Boolean operation that says, for example, unknown or true will give you true, right? But this is just because anything or true give you true, right? So this is why you can assume that, right? Okay. So as I warned you last time that some of you will be bored and some of you will be scared, right? But there is nothing to be bored about because there's plenty of things to learn, and there's nothing to be scared about because there will be the notebooks for you to learn SQL. And the one important thing this week is to learn SQL, if you just have to do one thing. All right. Then you need to do these to know these acronyms, DML, DDL. DDL is everything that has to do with defining the skeleton of a table. You say, these are my columns, these are my the types, this is an integer, this is a date. This is called data definition language. Data manipulation is when you fill your tables with data and you manipulate your data with select from where statements of SQL. So this is just a fancy name. You know what happens when people repeat terminology a lot? They start to use abbreviation, DML, DDL. It's the same with AI for artificial intelligence, for ML, for machine learning, and so on, right? There's just acronyms everywhere. But if you ever see DML and DDL, now you will know what these actually mean. Okay. At the end of this course, probably in May or something, I'll show you that with index structures, you can massively accelerate the speed at which you query data. In fact, it's exactly the alphabetical list you find at the end of some books, where you have an alphabetically list of words, and that points you to the pages on which these words appear, right? Well, this is called an index, and we have something similar in databases. But that will come back to in the last few weeks, but it already existed in the 70s. Another thing to know, so I'm throwing so many things at you today, is that there's several scenarios when you deal with data. There is a scenario that is read intensive and a scenario that is write intensive. So you might be reading a lot of data, but you're not actually modifying it. Or you might be constantly writing to the system. If you have a database behind an online shop, it's likely to be write intensive. Why? Because you keep updating your inventory, people keep placing order, paying, and so on and so on. So it's going to be very write intensive. So this is PostgreSQL, these are all the good old SQL system. Read intensive means you just drop the data somewhere, it's a data set, you don't touch it, all you want to do is analyze it. In fact, in this course, we're going to be very read intensive, right? We are going to drop our data in a data lake, it's called the data lake, very fancy name, and we are just going to analyze it, but we will not update the data, right? This is why we don't care about normal forms, in fact. Okay, everybody's following? Okay. Now, I will show you a good feature of relational databases that we also kind of had to give up in big data because it's very hard to implement. Some people are trying to. This is called transactions. What it means is that if you go to your ATM to withdraw money, if anybody is still doing that today, you want to make sure that either you get the notes and it's deducted from your account, or you don't get the notes and it's not deducted from your account. Right? You want to tie the two together, but you don't want to be deducted from your account and not have the notes. And you also don't want to have the notes without being deducted from your account. Or at least the bank doesn't want that. Maybe you do, but the bank doesn't. So this is called a transaction mechanism. And I'm just showing you the high level. There's 4 keywords known as ACID. We love acronyms, ACID, ACID. And I'm going to tell you ACID what they mean. A is what I just told you about the ATM. Either you get the notes and it's withdrawn, or you don't get the banknotes and it's not withdrawn. So it's all or nothing. This is called atomicity, right? So you want to tie multiple queries together, and either they're all applied or none of them is applied. Consistency means that you want your database to be consistent. For a bank, for example, they might want your account to be in the positive, or they might want the sum of some numbers to match some other numbers, right? This is called consistency. Before and after a transaction, you want to be consistent. Your account was positive before you withdrew money, and it's still positive after you withdraw money. So this is consistency. Then we have isolation. When you're a customer of a bank, there's millions of people using the bank and withdrawing at ATMs at the same time, but you want to feel special. So when you are at the ATM, it's as if you were the only person in the world actually accessing the bank database. Of course, you're not. There's millions of other people, but it's as if. So this way that a relational management system makes you feel special alone using the system is called isolation, right? You're protected, and you don't even feel that other people are writing to the database at the same time. And finally, durability is that you don't want the data to be wiped out and disappear suddenly, right? If you apply updates to your database, you want them to stay there, right? For example, if you store your data in the cloud, durability means that if you come back 1 week later, the data is still there and it didn't evaporate suddenly. Durability. So you see, A-C-I-D. This is called ACID. And this is something we get for free with good old relational database systems. Sadly, it's very, very, very tough to implement for big data when you have huge quantities of data. So as we will see during the course, it's just like the normal forms, we kind of throw that away because it's very tough to do. So you see, will not always be atomic or consistent or isolated and so on. But we want to be durable still. Maybe this one is more important than others. Okay, you made it, you survived this brush up lecture, which, as I said, was special because it's a lot that I'm throwing at you. But again, if I summarize, the one task you have is to learn SQL. This is the one most important thing. Take the time to learn SQL. The rest, many of these things will anyway come back during the semester to many of the concepts and put them in the context of big data. So you don't need to be too worried. But please take the time to learn SQL if you don't already know it and solve the exercises that the TA team prepared for you. So what's next in the course? Well, now that we saw tables that have rows and columns, in big data for engineers, because it's called big data, we're going to see tables with lots of rows. We're going to see tables with lots of columns, and we're going to see tables. I warned you about that. We're dropping the first normal form. We're dropping atomic integrity, lots of nestings, tables in tables in tables in tables, right? So this is big data, and big data. 3 different ways to have big data. And you'll see these are the weeks that we're going to have during the semester. And you see, depending on the week, we have lots of rows, lots of columns, or lots of nesting, right? That actually concludes the brush up. And now we are going to start with actual material very soon with cloud storage. Do you have any questions? Anything that isn't clear? No questions? Let me do a quick poll just to get a feeling. Who was bored because they already knew all that? Some of you? Yeah, I assume those who visited information systems for engineers, right? Because we covered it there. So you were bored. Who was scared that I threw all of that at you? Oh, nobody was scared. This is awesome. This is awesome. Okay, so I'm glad that I was able not to scare you too much. Okay, so please learn SQL. If you have questions, come back also on the Element chat or on the Moodle forum. I think this is the official place, and we'll be happy to answer any questions you have. And again, we'll come back to all these concepts during the semester. All right. So I'm going to stop right here, the recording and the slides. Then I'm going to load the other set of slides for cloud storage, and we continue. So see you on the other sides.